Hello, welcome to the lectures on microprocessor and microcontroller. So in this lecture we will be talking about the instruction set of 8085 processor. Okay. First of all, what is instruction set? It is the collection of, let's say it is the collection of all available instructions. Okay, it is a collection of all available instructions, and based on certain criteria we can divide this in different ways. So one of the criterion is the size of the instruction. Okay, so divide this, based on this there will be a division. And then the other division is based on the functionality of the instruction, that is what the particular instruction does. Based on that we have around 6 divisions for the instructions. And then there is another division, it is called as the addressing modes, or let's say based on the type of operands used. Okay, this type of division is called as the addressing mode, and this addressing modes you have studied in detail. In fact, all of these you have studied in detail for the 32-bit MIPS processor in your last course. So let's therefore there will only be a brief outline regarding all of this. So let's move forward. Okay, so division based on size of instruction. Okay, so there are 3 divisions, that is 1 byte. Okay, that is the whole operand will be whole instruction will be having only 1 byte. Examples are move A comma B. The size of this particular instruction is 1 byte, and this is the machine code. Okay, so this is how this particular operation, this is the assembly language, this is how we write and how we read, but this is how it is stored in the memory. So therefore and it is only 1 byte, 78 hexa. Okay, 78 hexa. So the thing is that whenever the processor is fetching this instruction, it only needs to fetch this 1 byte. Okay, another example is add M. Okay, and the machine code is 86. Add M is adding a memory location with the accumulator and storing the result in the accumulator. And where is the memory location? Because we are not giving any memory location here, right? That is stored in the HL pair, and that is a special function of HL pair. Like when I discussed the register bank of 8085 processor, I had mentioned that HL pair is used as a data pointer. So this is how it is used. Okay, then we'll move on to the 2 byte instructions. Okay, for example, MVI A comma 7 FH. This is move immediate A comma 7F, that is you have to move this particular value into A. So this will be stored in the memory as 3E followed by a 7F. So this will be the first byte of the instruction, and this will be the second byte of the instruction. Let's say the address is increasing like this. Okay, 3E followed by 7F. So during the opcode fetch cycle, this 3 is fetched, and once it is decoded, okay, the processor will understand, okay, it is a move immediate to A, and there is the immediate value has to be read from the next memory location, and from there the 7F is read. Another example is add immediate 0FH. Okay, so how is it stored? C6 followed by 0F. This is how the address is increasing from here to here. So the lower byte is C6, and that is the opcode. Always the first byte is the opcode. So the processor will fetch this one, and after decoding it will understand, okay, it is an add immediate instruction, and the immediate value has to be read from the next byte. So it will be taken from OF. It will take the value as 0F. Okay. So the third type of classification based on size is there is a 3-byte instruction. Okay, let's see. For example, JMP 9050, that is jump 9050. Basically, the program counter is reloaded with 9050, and the program execution continues from this particular address. So how is it written in the memory? It is written as C3 5090. Okay, so C3 is the opcode and 9050 is the particular address, right? So that actually the opcode is taking only 1 byte and the address is taking 1 byte. In fact, if you see in this particular processor, most of the opcodes will be having only 1 byte size. It is a fixed length, I guess. So this is how a 3-byte instruction is stored and used. In the first opcode fetch cycle, this particular value will be taken, and when it is decoded, the processor will understand, okay, it is a jump instruction, and it has to fetch it has to read the next 2 bytes in order to get the address to which it has to jump. Therefore, it will read 90 and 50. Okay. Another example is load accumulator 8850. So it is 3A 5088. Okay, but how can you load 8850 into accumulator? Because accumulator is a 8-bit register, right? So actually this 8850 is an address location. It is a memory location. It is not a value to be, this is not the value to be loaded into A. So what happens is that the processor, after decoding this value, will understand, okay, what comes, the next 2 bytes represent a memory location, or the next 2 bytes is an address, and it will go there and fetch whatever value is here, and it will take that and put it into the accumulator, right? So this is the classification based on the size of the operation or instruction. So there is 1 byte, 2 byte and 3 byte. Okay, so the next classification is based on the let's call it the type of instruction, which is based on the functionality. Okay, it's based on the functionality. So the first one in this category is the arithmetic instructions. The name is self-explanatory. For example, add, subtract, increment, decrement, decimal adjust after addition, etc. Okay, the second one is logical type of instruction. Again, the name is self-explanatory. OR accumulator, XOR accumulator, AND accumulator, rotate accumulator left through carry, rotate accumulator right through carry, compare, complement carry, like that. Okay, the next one is data transfer. Okay, so when we are talking about this data transfer type of instruction, we are not considering the data transfer from input output devices. We are only considering the data transfer from between registers and memory and register. Okay, that is from memory to registers, or from registers to memory, or between registers. That type of data transfer only we are considering. Okay, for the examples for this one is move, LXI, LDA, SHLD, and so on. So many other. So you might be thinking like I'm just going on just writing instructions, because later in this lecture I'll give you a chart of all the instructions available in 8085. You don't have to memorize all of them, but the thing is that I'll show you how to read from that chart. So whenever you are programming using an 8085 processor, you will know, okay, how to find a particular instruction which will suit your particular purpose. Okay, so the next is branching. Branching means that is whenever you want to change the flow of the program, you want to change, like usually it will be the program is executed sequentially, right? If the instructions are stored in the memory like this, and the execution will be like this, in this order, something like this. Okay, it will be going from one side to the other. So that is a sequential execution. So branching is used to disrupt this flow, and for example, from this point you don't want to execute this instruction, you want to execute this, so you can use a branching instruction to jump from here to here. So that can be conditional or unconditional, right? That is, you can just tell the processor to jump, or you can use a condition and say that, okay, if this particular condition is met, do this, jump to this particular. So jump is an unconditional jump, it will jump whatever the point is. Then JC, JM, JPE, and so on. One more thing, call. Okay, so all these are like, this is an unconditional jump, these are conditional jumps, jump carry, jump minus, jump parity, even things like that. This is a call. Call is used to call a subroutine. Okay, subroutine is something like, you can identify something like a function. That is, the thing is that suppose we have some instructions, we have a call here. Okay, and call means the execution of instruction will jump to some other point and will execute like this, and at the end of this subroutine there will be a return instruction. As soon as the processor sees the return instruction, it will jump to the instruction next to the call instruction and start executing from there. This is the specialty of call, because for jump and this conditional jumps, no such thing as it will just jump, it is just a branching. But this call means there should be a return value, because that is the purpose of using call. So whenever a call instruction is met, the processor pushes this particular address into the stack, and whenever the return is met, the processor retrieves the address from the stack and loads the program counter with it and jumps back to this particular address and continues the execution. You can use call as just a jump. It will jump, there is no problem. It won't look for a return, but there is no purpose in it. If you're using call as just a jump, you already have a jump for that. Okay, the next one is machine control. Okay, the examples are halt, no operation, disable interrupt, enable interrupt, set interrupt mask, read interrupt mask, things like that. Okay, so from some of your previous lectures you might remember that SIM and RIM can be used for serial communication, but that is not its primary purpose. It is to set and read interrupt mask. What are interrupt masks? Interrupt mask is used for masking of interrupts, right? Remember what is maskable and non-maskable interrupts are. So halt means the operation is halted. No operation is done. Just it will waste some clock cycles. This is to disable interrupts and this is to enable interrupts. The idea is that these are not for any purpose like branching. These are not for any of the previously mentioned purposes. These are to control the machine. These are to do some sort of, let's say, administrative work within the processor. The term administrative work is very casually used. Okay. The next one is I/O operation. I/O operation means to read and write from an input-output device, and it is done using in and out instruction. Okay. So this is the division based on the functionality of the different instructions. So now the next thing is addressing modes. Okay, so addressing modes is what is addressing modes? It is a classification based on the operands. Okay, operands for the different instructions. So all of the instructions may not come here, as all of the instructions don't have operands. For example, this machine control, it may not have any operands, right? So it only the instruction which works on some operand will come under addressing modes. Okay, so you already know what the different addressing modes are. So let's see the addressing modes available for 8085 processors, and different processors have different addressing modes. So the first one is register addressing mode. The operands used are, let's call this the operands. The operands used are registers or register pairs. Okay, register or register pair. Example is move AB, add B, right? Increment B, decimal adjust B, things like that, add B, INX B, things like that. So the thing is that in all of these the operands are registers. Okay. The next thing is direct addressing mode. So what are the operands in direct addressing mode? It is memory. Okay, so in this case all of the operands should be registers. Here all of the operands need not be memory. At least one should be a memory. For example, LDA 9250. Okay, here one of the operand is memory, right? The next thing is register indirect. Okay, register indirect. So in this one also, the operand, ultimately the operand is memory, in the sense that we'll explain it with an example. LDAX B. Okay, what does LDAX do? It loads the accumulator with the content of the memory location pointed to by the BC pair. Okay, BC register pair. So the thing is that ultimately the data is taken from a memory location, but it is not directly given like in direct addressing mode. The memory location is stored in a register pair, and that register pair is given in the instruction, right? That is why it is called a register indirect addressing mode, but the operand is in fact memory. Ultimately operand is memory. Okay, the next one is immediate addressing mode. Means the operand is given in the one of the operand at least is given in the instruction itself. So it can be an 8-bit or a 16-bit operand. Okay, examples are MVI C, 72, move immediate C, 72, LXI B, 2341, right? CPI FF. So here if you see here in this and this instruction, it is 1 byte, that is 8-bit immediate data. Here it is a 16-bit or a 2-byte immediate data. And the last type of addressing mode is implied addressing mode. That is this operand is implied in the instruction. That is, it need not be specifically mentioned. For example, in PCHL, right, in PCHL, the value of HL is loaded into PC. That is, this instruction is PCHL, and it need not, the instruction need not specify what are the operands used. The other is also exchange. Okay, here also the processor knows which data to exchange. It need not be explained, right? Then other examples are rotate, accumulator, write. So it knows. It doesn't need to, you don't have to say RARA, right? So it knows. So these are the different types of classification of instructions. So the first one is based on the size, 1 byte, 2 byte and 3 byte. Then the type of instruction based on the functionality, that is arithmetic, logical, data transfer, branching, machine control, or input output operations. Then the thing is addressing modes. So this is not, you need not consider this as a complete classification of instructions, because only instructions having operands are coming under this classification. So the addressing modes are register type, direct type, register indirect type, then immediate type, and implied type. So now that we have seen the different classifications, we'll just briefly see a chart having the, this is the complete instruction set of 8085 processor. Okay, so I'll just show you how to read it. Okay, so here the instruction syntax is given, that is, for example, here add register. So the instruction you have to write, for example, if you want to add A and B, right, you have to write add B. Why not A? Because the definition of the instruction is add register to A. So whatever register you are writing here, it will be added to A. Okay, so add register to A. And where is the result stored? Like I mentioned before, 8085 is an accumulator based processor, and all of the arithmetic and logical operations, unless specified, the result will be stored in accumulator itself. Okay, for example, this one, add M, add memory to accumulator. So we have to specify the memory, not here in the HL pair. So this is the syntax right? This is the syntax, this is the description of the instruction. This shows what the particular instruction actually does. Okay, then this is the code. Code means how it is stored in the memory. For example, ACI data. What is ACI data? Is add 8-bit data and carry to accumulator. So whatever data you are giving, for example, if you are giving ACI F0, okay, what happens? F0 plus carry plus accumulator. This sum is done and it is stored in the accumulator. That is the functioning of this instruction. So this CE, it is the opcode, right? This is the opcode of the instruction, and this data, this particular data, whatever you have to add, that is given following the opcode. So CE followed by the data. This is how the instruction is stored in the memory. Okay, then this is number of bytes machine cycles. How many machine cycles? Okay, then this T, this is number of T states. Okay, so number of T states, if you remember, it is the number of clock cycles, right? So if you observe, instructions having the same number of machine cycles may have different number of T states. Okay, you can find examples. For example, here 2 machine cycles are there, but 5 T states are there. Here 2 machine cycles are there, but there are 7 T states. This depends on the type of machine cycles, right? Because different machine cycles have different T states. Okay, so this is the description regarding which machine cycles are there for this particular instruction. Okay, so always the first machine cycle should be a fetch. Okay, the legend is given here. Okay, so if you see, in some it is given F and some it is given S. So you can see what is the difference here. F is fetch with 4 T states and S is fetch with 6 T states. That is, it is a special fetch. Some extra functionality is done there in an S type of fetch. Okay, so that is the different types of machine cycles coming here. Then this part, this shows which of the different flags are affected. Okay, so we have discussed about the different flags: sign, 0, auxiliary carry, parity and carry. So this chart shows how the different flags are changed or affected for each instruction. So if it is a tick mark, it means that based on the result, the particular carry is particular sign flag is affected. If it is a specific value, then no matter the result of the instruction, once the instruction is done, the value of that particular flag will be this. Doesn't matter what is the outcome is, right? If it is not mentioned, it means that particular flag is not affected for that particular instruction. Okay, this is how you should read this chart. Okay, this chart I will provide in the classroom. Don't worry about that. So I'm winding up this session on different instructions. So we'll see some of the commonly used instructions once we do some assembly language programming examples. Okay, so I'm stopping this lecture here. In the next lecture, we will start with the peripherals of 8085 processor, and after that we will do some assembly language programming examples, and we'll wind up the portion or topic of 8085. Thank you.